Hey there, if you love understanding exactly how things work under the hood, you are absolutely in the right place. In today's explainer, we're breaking down a really fascinating academic engineering proposal from the 2024 to 2025 academic year. We're going to crack open the blueprint for a low-cost, high-tech smart door security system. Now, this isn't just about theory. It's a super practical, real-world application of microcontrollers designed to solve the everyday vulnerabilities we all face. We're going to see exactly how these little components talk to each other to keep a space totally secure. Okay, so here's our roadmap for this explainer. We're covering the flaws of traditional locks, the smart door solution, the hardware behind it, the step-by-step system logic, storing the evidence, and finally, the final verdict. Let's get to it.
Part 1. Flaws of traditional locks. Let's kick things off by looking at a pretty universal vulnerability in our everyday security, the standard door lock. Traditional locks, well, they just give you basic access, but they have this massive blind spot. They don't record who opened the door, or even when, and if someone punches in a wrong pin on a basic keypad, completely ignored. But the proposed smart system totally flips this dynamic. It gives you secure pin access, sure, but it adds real-time human detection, timestamps images, and actually gives you immediate audio alerts. It's basically replacing blind trust with hard, concrete data.
Moving on to Part 2, the smart doors solution. So what's the master plan to solve those vulnerabilities? Well, the core objective of this project is actually super focused. The goal isn't just to build some flashy, wildly expensive gadget. No, they want to engineer a completely accessible, low-cost solution that gives you absolute proof of access. The brilliant part is designing a pin-based smart lock that doesn't just open a door, but specifically uses real-time human detection before it snaps a picture. I mean, think about it. That detail is absolutely crucial. It makes sure the system isn't just wasting storage space taking photos of an empty hallway, but actually saving it for real security events.
All right, Part 3, the hardware behind it. Now, what makes this whole setup so interesting is its dual microcontroller architecture. It basically acts as the brain and the eyes of the operation. First up, the brain. You can think of the ESP32 DevKit V1 as the bouncer of our system. When you walk up to the door, this is the guy you're dealing with. It reads your PIN from a 4x4 keypad, validates those numbers against its stored credentials, and if it likes what it sees, it triggers a relay module to physically unlock the door. But here's the kicker. Once it unlocks the door, it doesn't just clock out. It actually sends a trigger signal to our second component.
And working in perfect tandem with our bouncer is the ESP32 CAM, which is basically our vision unit. Now, this unit just sits quietly until it gets that signal from the main controller. And when it wakes up, it doesn't just blindly snap a photo. It actively runs real-time human detection using an OV2640 camera module. Only when it verifies, yes, there is an actual human being standing right there, does it capture a timestamped image. It's a really smart two-step process to guarantee accuracy and completely avoid false alarms.
So here is the complete hardware blueprint for the whole shebang. And honestly, notice how standard and affordable these electronic components are. Aside from our two microcontrollers, the entire system relies on just a single 4x4 keypad, a simple buzzer for alerts, and a solenoid or servo lock that's controlled by a relay module to actually hold the door shut. Add in a standard 5-volt power supply and a microSD card to act as a local vault for the images, and you're set. It's proof that you absolutely do not need proprietary, wildly expensive hardware to build a rock-solid, intelligent security device.
Which brings us to Part 4, step-by-step system logic.
Now that we know what's under the hood, let's test this out with a little if-then storytelling to see exactly how the system reacts when someone actually approaches the door. Let's start with the best-case scenario. You walk up, you punch in the correct PIN. Bam, the bouncer goes right to work. The door unlocks, and you get this comforting little short success beep. And while you're turning the handle, that ESP32 cam is already scanning for you. It spots you, silently captures a timestamped photo, and locks it away. Just a perfectly seamless, fully tracked entry.
But what if you're an intruder? Let's say you just punch in some random code hoping to get lucky. Well, the bouncer instantly spots the fake credentials. That door, it's staying firmly locked. And instead of a welcoming little chirp, you get hit with a harsh, long warning beep. So the system denies you entry. But behind the scenes, it is definitely keeping track of that failed attempt.
And the engineering proposal actually explicitly highlights these audio cues because sound is just so incredibly important for user feedback. A correct PIN gives you a short double beep, kind of like a beep beep of success. An incorrect PIN triggers that long single warning beep. And later, when you close the door and it secures itself, you get a single short confirmation beep. The beauty here is you literally never have to guess what the lock is doing. The system is constantly talking to you. Now, if an intruder is being particularly stubborn, This system definitely has a breaking point. It tracks exactly 3 consecutive wrong PIN attempts. The very second that third bad code is entered, the system totally escalates from a simple warning beep to a continuous blaring alarm that goes off for 5 full seconds, immediately drawing attention to the door.
Moving on to part 5, storing the evidence. Okay, so the door stayed locked, the alarm went off, and the camera snapped the intruder's picture. But where is that evidence actually going? The proposal outlines 3 really adaptable storage methods. First, you can just use a microSD card directly inside the ESP32 cam. This is super fast, totally local, and 0 internet required. Or you could use Google Drive or Firebase for a cloud backup, which is awesome if you want to check it from your phone anywhere in the world. And third, for bigger setups like a college lab, you can link it to a local PHP and MySQL server. But the absolute best recommendation for long-term storage? A hybrid approach. Store the images locally on the SD card for that immediate fail-proof backup, but then have the system automatically upload the crucial images to a cloud server whenever Wi-Fi is available. Because when it comes to security, redundancy is everything.
Finally, part 6, the final verdict.
So the real takeaway here is understanding what all this hardware and logic actually accomplishes in the real world. This project takes basic, off-the-shelf microcontrollers and turns them into a highly reliable, incredibly smart security system. Just think about the perks we've talked about. It's remarkably low cost. It gives you absolute time-stamped image proof with real-time human detection. You get crystal clear audio feedback. You have remote cloud access. And maybe the biggest game changer is its modular design. Because it's built on these flexible ESP32 boards, the proposal points out that you can easily code in future upgrades like face recognition, mobile app alerts, or even one-time passwords later on. It is practically tailor-made for homes, labs, or small offices.
It really makes you wonder, doesn't it? We've just explored how an academic project can take a handful of standard electronic parts, wire them together, and completely eliminate the blind spots of a lock design we've been using for over a century. So, if you can build a highly secure, vision-enabled smart lock with basic, affordable microcontrollers, what other everyday vulnerabilities are just waiting to be engineered out of our lives? It's an absolutely fascinating blueprint, and a great reminder that the tools to upgrade our world are more accessible right now than they have ever been. Thanks for hanging out with me on this explainer, and until next time, keep questioning how things work.